A scientific model is only as good as its ability to explain known phenomena in the field that it represents. And so we, in our last video, looked at Bohr's features in his planetary model, and it's great. You know, it is not the most modern version of the atom. The power of his model, what makes it valuable, is that he was able to use it to explain a few things of real importance that were not fully understood by chemists. Number one is something called periodicity. And in this video, we're going to cover that. And second, we're going to look at line spectra that we saw in things like gases that were heated up and then resolved using a prism. Um, let's focus on periodicity here. The idea of periodicity is something that we've already talked about before. With elements on the periodic table, there is a repeating pattern of chemical and physical properties that up until this point hadn't really been explained. We could put elements into groups or columns on the periodic table because they have chemical and physical properties that are similar, but we don't have a rationale for why that similarity exists. That is until we start using Bohr's model as a way of explaining how those similarities begin to appear. Take, for instance, two elements that show up in group one of the group one of the periodic table. Group one, you'll remember, are the alkali metals. We've seen that they are soft metals that can be cut with a knife pretty readily, that if you put them into water, they will produce hydrogen gas and catch on fire. So all of them, lithium and sodium, potassium, rubidium, cesium, all have very similar properties. That's why they're in group one. Bohr's model says here's the reason they have similar properties. If I look at lithium and sodium, for instance, at first, they don't appear to have all that much in common. Lithium has 3 protons and 3 electrons, and sodium metal has 11 protons and 11 electrons. But if we follow the features of Bohr's model, you know, one of the things that he said is each orbit has a specific capacity of electrons based on a 2n squared rule. That's how many electrons you can fit. And the second thing is that you should fill the lower orbits before you fill outer orbits. So if I look at lithium and sodium, I can fit 2 electrons into the first shell. In the second shell, 2n squared tells me for sodium I can put 8 electrons total. And then each one of these elements has leftover electrons that would go into an empty shell and would not be filled to capacity because at this point I'm seeing 2 electrons in lithium and 10 electrons in sodium. They each have one leftover electron. And so in the outermost shell for sodium, we're going to put 1 electron, and that gets us to a total of 11 electrons. For the outer shell of lithium, we're also going to put 1 electron. That gets us to a total of 3 electrons. And this is what Bohr said. The reason that elements have similar chemical and physical properties is that their outermost shells are similar in terms of the number of electrons found there. We call that the valence shell. And as we're going to see, it's really these valence electrons that have everything to do with things like chemical reactivity. So as long as elements have similar valence shells, they should have similar properties as well. Take a second look at another example. Let's look at the halogens. The halogens are group 17 on the periodic table. Chlorine has 17 electrons, fluorine has 9 electrons. How could it be that they would be similar? But as we start to fill up our electron shells, it turns out that chlorine has 7 electrons in its outermost or valence shell, and so does fluorine have 7 electrons in its outermost shell. These elements are similar to one another because because they have similar valence shells. But with any model, you're always going to run into challenges. What you find is that Bohr's model works well at explaining periodicity up to a point. It really starts falling apart after the 18th element. Okay, so up until we get to argon, you can use Bohr's model to predict periodicity. But we're going to find, starting with the 19th element, which is potassium, things start to fall apart and you don't have the correct number of electrons in the valence shell. And that's how science works. You find flaws and then you come up with refinements for your model and look for experimental evidence that supports it to produce a newer and better model. So yeah, Bohr's model does a great job for the first 18 elements, but we needed to do a great job for 118 elements. We needed to be able to explain what's going on with all elements on the periodic table. So we'll get there eventually, but so far, so good with Bohr's model. See you next time.